Okay, I'll get started. Just wanted to begin with a reminder that 1 week from now, so next Thursday, March 13th, is Test 2. Test 2 has exactly the same format as Test 1. Test 2 has 3 fully worked out problems worth 80%. It has 10 true-false worth 20%. It covers all the material that's listed here since Test 1 up to Test 2. So these are seven lectures here. Any questions on all that? Okay, if you get any questions over the next days, then you can just email me, and I'll try to answer them. Want to move on with the material for today's class. Today's class is all about what we call transformer induction. Last class was all about what we call motional induction. Both transformer induction and motional induction are magnetic examples of magnetic induction, but motional induction involves moving parts. Transformer induction doesn't involve moving parts. So I'm going to start with some illustrations, examples of transformer induction and transformer EMFs and transformer currents. I'll then introduce some new words, some new quantities, some new ideas related to what we call inductors and inductance. And we'll see they kind of parallel, kind of resemble capacitors and capacitance. Then finally I'll talk, like we talked about, energizing capacitors, de-energizing capacitors and the energies they store. We'll talk about energizing inductors, de-energizing inductors, and the energy they store. So those are the topics for today. This is just to point out an interesting thing about Faraday's law. It's a very, very special law in the world of physics. It's a very, very special law in the world of physics because it's the only law we know of, that describes two different effects, phenomena. It describes the effects that we met in last class of motional magnetic induction, where there's moving parts, that has one origin. It describes the effects that we're going to describe in this class. It's transformer induction, where there's no moving parts. It actually has a different origin. So it's a very interesting law in that the single law, the single equation, actually describes two different phenomena, two different effects beneath the law, underneath the law. So I wanted to mention that, just in case you're interested. Okay, physicists love that fact, but outside of physicists loving that fact, maybe it's unimportant. Transformer induction. I'm going to talk about transformer induction between a pair of circuits, two separated circuits. Then we'll actually talk about transformer induction involving just a single circuit, just one circuit. So that's a path here. So the basic idea is that transformer induction is the fact that circuits, two circuits that are disconnected, unconnected circuits, will actually communicate or talk to one another. Here's an example. I've got a circuit on the left-hand side that I can switch on and switch off with this switch here. I got a circuit on the right-hand side, and I've got a voltmeter or an ammeter, some sort of meter to measure activity in this circuit. And what we've discovered, this was actually Faraday's experiment, it was his very first experiment on magnetic induction, is that when you switch on the circuit on the left-hand side, at that moment you induce an instantaneous, momentarily voltage, current in the circuit on the right-hand side. That's induction. When you switch off the circuit on the left-hand side, you also momentarily, instantaneously induce a current and an EMF on the circuit on the right-hand side. That is circuit number one talking to circuit number two. They're communicating. And circuit number two also will talk to circuit number one. If we switched it on or off, then it would communicate with circuit number one. And so that's in induction. Here's an example of induction, how you might use induction. So inside your bodies, my bodies, are electrical components. A big important one is our brain. Another one, important one, is our hearts. Those are electrical devices. Those create electrical currents, electrical voltages. Those electrical currents and voltages are turning on and off as our neurons sort of activate and relax, or our heart pumps away. They produce time-varying currents, time-varying magnetic fields that you can detect, you can observe in a neighboring circuit. If I put a loop of wire near your head or near your heart, we could detect the switching on and off of currents in your head or in your heart in a neighboring circuit. And so this is one application, one medical application in diagnostics, for example, of magnetic induction, is to detect currents, voltages in your heart, in your brain as they change, as they vary. And it's magnetic induction. I want to show you an example of magnetic induction. When we detect the currents in your brain with magnetic induction, those are tiny currents, little fluctuating currents. They're quite hard to see above the ambient electronic noise that's around us. When we detect the changing currents, changing voltages in your heart, those are small currents, small voltages. They're quite hard to see above the ambient electronic noise. But I want to show you an example of two circuits talking to one another, communicating with one another. That's much, much easier to see. So we're going to take a look at this. The demonstration's over here. There's a sketch of it here. It involves two circuits. So this demonstration involves two circuits. There's one circuit is this long solenoid here, and a second circuit is this this coil here. And you can see these two arrangements here. In red, that's the long solenoid, and the copper turns here. That's the coil. Now I'm calling one a solenoid and one a coil because the solenoid has many turns. So our solenoid happens to have 1,000 turns. The coil has just a handful of turns. It has 10 turns. So we've got a solenoid and a coil, they're disconnected from one another. They're physically disconnected from one another, although the solenoid is obviously sitting inside the coil. So this is an example arrangement of two circuits where if we would turn on a current in one circuit, or switch off a current in one circuit, we'd expect to see a induced voltage and induced EMF in the other circuit. That would be an example of magnetic induction. Actually, what we're going to do, we're going to turn on a current in the larger coil, the larger diameter, smaller number of turns coil, and we're going to look for a induced EMF, an induced current in the solenoid. And these two horns, they kind of look like to me, out of like a Frankenstein movie or something like that, they are connected to the two ends of the coil. And so they might show us if there's a induced EMF that's created, produced across the coil. So I'm going to switch this on. I think maybe we'll set the mood. We'll turn some lights out. And what I'm going to do, I've got a foot switch here to switch it on. But what I'm actually doing, when I press the switch, the current in the outer coil that's going to induce an EMF in the inner solenoid, that current in the outer coil is going to be switched on and off very quickly. So it's a large current in the outer coil, and actually when I press the pedal, it's going to be switched on and off. I think it's like 200,000 times a second. So it's going to be switched on and off very fast. I obviously couldn't do that myself. So that there's a circuit that will switch that current on and off 200,000 times a second. So I'm changing the current in the coil very, very rapidly. I'm switching it on and off very, very rapidly. I'm switching it on and off very, very rapidly, so I create a large induction effect because it depends on how fast or slow you turn on and off the circuit. So let's try this out. So that's a large voltage. That's a large voltage that I'm generating because of several factors, right? That's a large voltage that I'm generating because I'm switching on and off a current extremely fast. And the induced EMF, the induced current, depends on the rate of change of the voltage or the current in the circuit. And I'm making that rate of change very large. That voltage is also very large because I've got this solenoid that has many, many turns. And each of those turns captures some of the flux of the coil. And if I've got 1,000 turns, I capture 1,000 times the flux of the coil. So this voltage is so large. It's tens of thousands of volts I'm producing. It's so large that the air simply burns due to that voltage. It's simply ionized like lightning due to that voltage. And it's entirely because I'm changing the current very rapidly, and I've got lots of turns of the solenoid. Okay. I want to do a little calculation related to this demonstration. We're going to calculate the induced EMF that we just saw. So we just saw an induced EMF in the solenoid, and we're going to calculate an induced EMF with exactly this arrangement, based on Faraday's law of induction. Now, in the demonstration, I had a current that was switched on and off in the coil, and we observed the voltage that was induced in the solenoid. So the starting circuit is the coil that I'm switching on and off. the circuit that sees the effect, the cause, is the solenoid. I'm going to reverse that for the calculation. I'm going to reverse that for the calculation for a very practical matter. It's hard to calculate the flux through the solenoid due to the coil because the magnetic field and magnetic flux of a coil is rather complicated. But it's much easier to calculate the flux of the solenoid, which produces a simple magnetic field and a simple magnetic flux through the coil. So we're going to calculate the induction of the solenoid on the coil rather than coil on the solenoid as we solve this problem. But the important point is that when you have two circuits that talk to one another, they talk equally well to each other. So actually the amount that the solenoid talks to the coil is the same as the amount that the coil talks to the solenoid. It's changing the current in the solenoid by a certain amount has the same effect on the coil that changing the current in the coil has on the solenoid. And so although I am solving the reverse problem because it's one that's practical, the other one's impractical, I'm actually solving in one go both problems. How much the coil talks to the solenoid and the solenoid talks to the coil. Anyway, let's get on with solving this problem. I'm going to adjust the lights a little bit. In this overhead, on this overhead, we're given the details of the coil, the solenoid, and the changing current. So we're told, for example, the solenoid has 1,000 turns. It has a cross-sectional area of 0.05 meters squared. It's 1 meter long. We're told that the coil has a radius of 0.3 meters and it has 10 turns. And then we're told the current and how fast we change the current in the solenoid. So the current in the solenoid goes on and off in 2.5 microseconds, and on is 125 amps, off is 0 amps. So we're going to use all that information. I'm going to switch to the document camera and we'll solve this. I made ahead of time, of course, I made a little picture. This is a cross-sectional view now. Like a cross-sectional view. Here's the solenoid. That has the smaller radius. Here is the outer coil. That has the larger radius. I've given the solenoid a subscript 1. It's circuit 1. That's what we're going to change the current in. I've given the coil a subscript 2 because that's where we're going to see the induction. So upstairs here, I've listed all the quantities I know about the solenoid. We know the number of turns, N1. We know the cross-sectional area, A1. We know the current change in the solenoid, I1. Oops. And we know the time that current was changed in. And then I did the same thing for the coil down here. We know the number of turns of the coil is 10. I call that I2, that you can't read at all now, N2. And we know the radius of the coil, that's R2. So that's all the information we're going to give, that we were given. I'm going to solve this problem of what is the resulting induced EMF in the coil. That's our target. What's the result in induced EMF in the coil? By first figuring out the change in magnetic field in the solenoid when I switch it on and off. Then figuring out the change in the flux in the coil when I switch the solenoid on and off. And then that'll lead me to the EMF that's induced in the coil when I switch the solenoid on and off. So my route is changing magnetic field of the solenoid, changing flux through the coil, induced EMF in the coil. So that's my path. The change in magnetic field in the solenoid I'm going to call it delta B1. It's the difference between the current being switched on and the current being switched off. The magnetic field in a solenoid, if you remember, is the product of mu naught times the number of turns of the solenoid times the current in the solenoid. What we're interested in is the change in the magnetic field. So I'm interested in the change in current, and so the change in magnetic field is mu naught times the number of turns times the change in current. All those quantities we know. Mu naught, that's that constant of nature, is 4 pi times 10 to the minus 7 Teslas, meters, amps. I won't write it down. N1, that's the number of turns of the solenoid. That was 1,000. The change in current, I1, we wrote that down as 125 amps. So I just got to plug all those numbers in. And if you do that, you get a magnetic field in Teslas. I got 0.157 Teslas. So that's the field inside the solenoid when it's switched on. It's the change in field when I switch on to off or off to on. We said that was our first step. We said the second step would be to calculate the change in flux. Phi is the flux, delta phi is the change in flux. The change in flux in the coil. That's the subscript 2. So I want to calculate this change in flux. What's the change in flux in one loop of wire? It's the area of the loop times the change in field times cosine theta. That was our equation for flux or change in flux. So area times field times cosine theta is at flux or change in flux due to change in magnetic field. That's in one loop of wire. If I got multiple loops of wire, I got to multiply by how many turns we have. Now let's be careful with the subscripts here, and let me clean up this mess I just created. The number of turns is the number of turns of the coil. Now we're thinking about the flux through the coil. So that's the number of turns of the coil, that's N2. The area, I might be tempted to write the area of the coil, but I'm going to write the area of the solenoid because the magnetic field only exists over the cross-section of the solenoid. It doesn't exist outside the solenoid. So when we calculate the flux from the field, we've got to multiply the field inside the solenoid by the area of the solenoid to calculate the flux through the coil. So this is actually A1, and this field is B1. It's the field due to the solenoid. And then I'm going to multiply it by cosine theta, but the field is out of the page or into the page. It's perpendicular to the arrangement of the coil and the solenoid, so this is just going to be a 1. Okay. I know the number of turns of the coil is 10. I know the change in magnetic field of the solenoid is 0.157 Teslas. I know the area, cross-sectional area of the solenoid is 0.05 meters squared. Plug in all those numbers. Again, I'm not writing them down. I'm already completely panicked and anxious about, I never get this class over before 5 o'clock today. 0.078 Webers. That's the change in flux. Change in flux through the coil due to the change in magnetic field in the solenoid. Now we're almost there. The EMF induced in the coil, so a subscript 2, is the change in flux through the coil, so delta phi 2, divided by the time interval over which that change occurred. We know both of these. We know the change of flux is 0.078 Webers. We know the time interval to switch the circuit on or switch the circuit off was 2.5 microseconds. We were given that piece of information. Here it is upstairs here. And so if I plug in those two numbers, I'm dividing 0.078 by 2.5 times 10 to the minus 6 seconds, you get 31 kilovolts That's the voltage that's generated across the coil when the current changes in the solenoid by this amount. That's also the voltage that's generated across the solenoid when the current in the coil changes by that amount. And that's the voltage that we saw that was breaking down the air like lightning. That was the 31,000 volts, and that's why those seats are all, you don't sit in those seats with that demonstration. Okay. Everybody okay with that? Quiz question. That even surprised me that it's so early. How did that happen? Surprised me so much I don't know what to do now. So the quiz question, sorry. The quiz question is about the type of arrangement we've just been discussing, right? There's an inner and outer coil and solenoid, for example. And we're told that the induced, what are we told? I've got to read it. What is the direction of the current in the rectangular loop as the counterclockwise current in the solenoid, that's the outer circular loop, increases from 0 to 3 amps? So we're switching on the current here in this outer loop, which is what was done in the demonstration. We're inducing a current in the inner solenoid. What direction is that induced current? So I'll give you a moment to think about it. So this is an example of Lenz's law, which lives within Faraday's law, which describes magnetic induction. And remember, Lenz's law said that the induced magnetic field, when you've got induction, opposes the change in the original magnetic field that created the induction. So in this particular example, the original magnetic field, the changing magnetic field that's going to create the induction, is the current in the outer loop that is shown in the sketch. So there's a current in the outer loop, that's the solenoid, and that current in the outer loop is going counterclockwise and is producing a field that's out of the screen towards you, and that field is actually shown in this sketch, right? The little dots, the little turquoise dots are showing you that there's a field that's produced by that current that's out of the screen. So suddenly this current starts circulating around counterclockwise that produces suddenly a magnetic field that's streaming towards you. What does Lenz's law say about the induced current? It says it's going to try and oppose that change. So the induced current is going to want to make a magnetic field that's into the screen. If I point my thumb into the screen, that's the direction of the induced magnetic field, my fingers curl in the direction of the current in the inner coil, in the inner rectangular coil that must make that current. And they're curling clockwise. And so we would get a clockwise current in that inner rectangular coil if we switched on a counterclockwise current in the outer circular loop. And that's Lenz's law. It's an example that, you know, if you switch on a current and make a magnetic field, then the induced magnetic field will oppose that original magnetic field. The induced current kind of opposes the original current. We switched on a current that was counterclockwise. We're going to create a current that's counterclockwise, in opposing direction. Just like the magnetic field was out of the screen, we create a induced field that's into the screen. So just like the fields oppose one another, this is an example where we looked at the currents, and the currents oppose one another when you switch on the circuit. Okay, I want to talk about induction, transformer induction, not between a pair of circuits, but between within a single circuit. So it turns out that not just a pair of circuits will talk to one another through induction, but actually a single circuit will talk to itself. I mean, we all know that from, you know, human beings, right? I mean, I talk to other people, but secretly I sometimes talk to myself. Circuits do the same thing. They talk to one another, communicate with one another, but they also talk to themselves. So we're going to see a little bit about that. Here's an example of a single circuit. It's a solenoid, and I'm picturing on the left-hand side, the solenoid has been activated, and some current is flowing in the solenoid, but that current is that current's not changing. I'm picturing in the center, same solenoid, but now I'm picturing it at the moment that the current in the solenoid is increasing. So in the center here, the current is increasing. And then finally on the right-hand side, I'm picturing again the same solenoid with a current in it, but now that current is decreasing. So as you walk from the left to the right of this figure, on the left you've got a constant current, in the center you've got a growing current, and on the right you've got a falling current in the three pictures. Alongside the constant current, the growing current and the falling current is a constant magnetic field through the windings of the solenoid in this case. So this is the field and it's constant. In this particular case where the current is increasing, then the field would be increasing. The number of field lines would be growing as a function of time. And in this right-hand case where the current is decreasing, then that would be a case where the field is correspondingly decreasing. The number of field lines through the circuit is correspondingly decreasing. So bottom line is that in this left-hand picture where the current was constant, there's no change in flux through the circuit because there's no change in the number of field lines through the circuit. In this case in the center, there is a change in flux through the circuit because the current is growing. It's an increase in flux through the circuit. In this case on the right-hand side, again, there is a change in flux through the circuit because there is a changing current in the circuit that's creating the magnetic field, and it's a decreasing flux. And so I kind of summarize that here with change of flux being 0 on the left, change of flux growing, magnetic flux growing in the center, change of flux decreasing on the right-hand side, due to the fact that the current is constant on the left, increasing in the center, and decreasing on the right. Well, what do we know that a change in flux does, right? We spent 2.5 lectures on it now. We know that a change in flux induces an EMF. We know that it induces a current. And so in the center case, where we've got a growing flux, we're going to get an induced current, induced EMF. In the right-hand case, we're going to get an induced current, induced EMF. In the left-hand case, there's no change in flux, so there's no induced current and no induced EMF. What this is telling us is, if you have a circuit, just a single circuit, just like this one solenoid, if you change the current in it, you're going to induce an EMF and a current in itself. If you increase the current in it, you're going to induce an EMF and a current in it itself. And if you decrease the current in that circuit, you're going to induce an EMF and a current in it. And so that's what we call self-induction. Like self-torque, it's self-induction. It's self-induced EMFs, self-induced currents. And that's the effect I'm talking about here. To describe, so now I'm going to get quantitative. I'm going to get a bit more precise about, I might talk to myself a lot. You might, not very much. If in circuits, we use a quantity called self-inductance to describe a circuit and how much it talks to itself. If it has a large self-inductance, then that means that that circuit talks a lot to itself. Small self-inductance, it talks only weakly to itself. Talking a lot to itself means when the current in that circuit changes, you get a big induced EMF and a big induced current. Talking to yourself just a little bit, small self-inductance, means that you change the current in the circuit, you don't change much, don't get a very big induced EMF, don't get a very big induced current. So that's the idea of self-inductance. It's a measure, it's a quantity that describes the amount that this or that circuit happens to talk to itself. The self-inductance is defined by this little equation up here. So L is the symbol we give the self-inductance, and it's a proportionality constant between the cause of induced EMFs, induced currents, which is a changing current, and the effect, the result, which is the induced EMF. So if you look at and the change in flux. So if you look at this equation here, L, this self-inductance, is the proportionality between the changing current that you have in the circuit and the resulting change in flux through the circuit, which determines the EMF. And so it's this proportionality constant here. It's also really just the proportionality constant between the current, not just the change of current and the change in flux, but the proportionality constant between the current and the flux itself. So this is also a way you can define the self-inductance. As I say, the bigger the self-inductance, that means the larger the circuit talks to itself, the larger induced EMFs you'll get when you switch the circuit on and off. The smaller the self-inductance, the smaller the circuit talks to itself, the weaker the induced EMFs you'll get when you switch the circuit on and off. I want to show you a demonstration of this too. It's not going to be very dramatic after this one. This is rather small to see. I don't know if I can put it on a camera. Yeah, here we are. This is a circuit that's made up of a 9-volt battery. So here is where my finger is. That's a 9-volt battery, just a regular one. We got it from Kroger's. That circuit, follow this red wire here, goes through a switch. So I can this is a switch I can turn the circuit on and off with. After the switch, we go through a solenoid. So this is a solenoid, just like the smaller version of the solenoid over here. It has many, many, many turns. A solenoid is a circuit component that tends to have a large self-inductance. Current flowing in the solenoid creates magnetic field. All that magnetic field is bundled up inside the solenoid. There's many turns of the solenoid around that magnetic field. So the solenoid has a large flux for the current that's flowing through it. That's a large self-inductance. You change the current in the solenoid, you'll create a large change in flux through the solenoid. So this is something, think of this as somebody, somebody that talks to themselves a lot, somebody that has a large self-inductance. That's who a solenoid is. And then finally, after the solenoid, if we follow the circuit, there's a little lamp up here. And then we go back to the battery. So if I was to close the switch, well, you might think the current would flow through the solenoid, go through all the windings of the solenoid, then the lamp, back to the battery, and the lamp would light up. But there's a catch here in this circuit, that the lamp that we have here needs about 100 volts to light. The battery is 9 volts. So it's actually, if you think about it, you would think that it's impossible to light this lamp that requires 100 volts with this battery that only supplies 9 volts. So that sounds impossible. Why did you build this? Why on earth did you build this when you're building it with a 100-volt lamp and a 9-volt battery? It's never going to work. Well, it's never going to work. We're never going to light this lamp except for the moment that we turn on the circuit, the moment I close the switch, and except for the moment that I turn off the circuit. When I close the switch or open the switch, I'm changing the current in the solenoid. Current's growing when I close the switch, current's decreasing when I open the switch. At those moments we get induced EMFs, induced currents. And in this case, because of the large self-inductance of the solenoid, because it talks to itself a lot, the induced EMF is actually much bigger than the battery's EMF. The induced EMF is more than 100 volts, more than enough to light this lamp. And that's the crazy thing about this circuit. Although it's impossible to light the circuit with the battery, because it only provides 9 volts, you need 100 volts. The moment you switch it on, we'll see a flash of light from this lamp, because at that moment there's a big induced EMF that's more than 100 volts. The moment we switch it off, again, we'll see a flash of light in the circuit, because at that moment there's more than the 9 volts. There's more than 100 volt induced EMF due to the large self-inductance of the solenoid. Now, this has practical applications, you might be surprised to know. Cameras, we just use iPhones now, but cameras used to have flashes on them when you take a picture of your friends. Those flashes need a large voltage to flash that bright lamp. Well, the camera's got a 1.5 volt battery in it. It's never going to flash that lamp. This arrangement, where you can create a large voltage from a small voltage, at that moment you switch it on and off, is what flashes the flash on one of those old-fashioned cameras. And so there was at least one application of this. I've really got to turn all the lights out. This is not an overly dramatic experiment. And I'm just going to see if you can see the lamp flash on. I'm going to close the switch now. And I'm going to open the switch now. And I don't know if we see it up there. Don't think we see. Yeah, we do. I didn't realize that. So on, we get a flash. It's on now, there's nothing happening. The battery can't light it. Off, we get a flash. At that moment, that induced EMF lights here. Back on, we see a flash. Back off, we see a flash. Okay. So that's self-induction. Self-inductance, self-induced EMFs, self-induced currents, they can be large. They can be large. Here's a quick example of self-inductance. We're told that 24 millivolts is induced in a 500 turn coil by a rate of change of current that's 10 amps per second. Based on that information, we're going to calculate the coil's self-inductance, this quantity, this number that describes how much it talks to other circuits, and we're going to also then go on and calculate if we had a larger rate of change of current, 100 times bigger, what would be the induced EMF? So we're going to do these two things. I really want to do this fast. Okay. So I started this off, of course. Here's the sketch that goes with the problem. And here's my coil that I'm going to activate. So there's going to be a rate of change of current. And we're told that rate of change of current is 10 amps per second. And the result of that rate of change of current through self-inductance, through magnetic inductance, is that there's an induced EMF. And we're told that induced EMF is 24 millivolts. And we're also told 500 turns. So what is the self-inductance? Well, the key equation was that definition that defines self-inductance. It's the proportionality constant between the induced EMF, that's the rate of change of flux, E equals d phi dt, and the change in current itself, the rate of change of the current. So it's this equation that we met on a slide or two ago that defines the self-inductance. Now look, we know the rate of change of current, we know the induced EMF, so we can use this observation, you get 24 millivolts when you change the current by 10 amps a second, to calculate the self-inductance. So it would simply be 24 millivolts, so that's 0.024 volts, divided by 10 amps per second. And if we do that calculation, I got a value that's 2.4 millihenries. So it's 2.4 times 10 to the minus 3 henries. Henries was the unit of self-inductance. Remember Joseph Henry? We've got to thank him for all this self-inductance. And his name goes with the units of self-inductance, and it's 2.4 millihenries. Okay. Second part of the question was, well, supposing we have a redo on this project. We change the current again. But this time we changed the current by 100 times greater rate of change. So instead of 10 amps per second, we're going to change the current now at a rate that is 1,000 amps per second. What's the induced EMF in this case? Well, we can go back to our relationship between the induced EMF, the result, the effect, and the change in current, the cause, the origin. In this particular case, if we go back to our equation, induced EMF equals the rate of change of current times the self-inductance. Well, we know the self-inductance now is 2.4 millihenries, or 10 to the minus 3 henries. We know the rate of change of the current is now 1,000 amps. If I multiply one by the other, I'm going to get, actually, maybe I should have wrote this as 2.3 times 10 to the 2.4 times 10 to the minus 3 henries. So we've got 2.4 times 10 to the minus 3 times 1,000. That gives 2.4. This is 2.4 volts. And so that's the new voltage with this new change in current. We could have done that calculation, or we could have, I wish I'd saved time. I wish I'd said, oh look, the rate of change of current is now 100 times bigger. It was 10 amps a second, rate of change of current. Now it's 1,000 amps a second, rate of change of current. That's 100 times bigger. That just means that the induced EMF, the resulting effect, will be 100 times bigger. 100 times bigger from 24 millivolts is 2.4 volts. So I could have done it that way too. Okay. If you want an analogy to inductors, think of capacitors. That equation for inductance that says it was a proportionality between rate of change of current and rate of change of flux, or simply between current and flux, resembles a similar equation for capacitors, where capacitance is defined as a proportionality constant between the charge you put on the plates of the capacitor and the voltage you get between the plates of the capacitor. So in capacitors, right, you place charge on the plates. Inductors, you flow current through the windings. In capacitors, you get a voltage between the plates. In inductors, you get a flux through the windings. And so that's kind of the analogy. And so capacitance and inductance are the same proportionality constants, but in the world of charge and voltage versus the world of current and flux. So I just wanted to show you that. Like there was a special capacitor, well, we loved it. We loved this capacitor because it had a simple equation, geometrical equation for the capacitance. There's a special inductor, we love this one too, that has a simple equation for the inductance of the inductor in terms of the geometry. So for the capacitor, the special equation, I want to set the mood again, the special equation was for a parallel plate capacitor, where you just have two large sheets of charge, equal and opposite charge, opposite one another. You've deposited equal and opposite charge on these two plates. The capacitance is that equation there, epsilon naught A over D. So that's an old friend to us that we might remember. It says that the capacitor of that parallel plate capacitor depends on how big the plates are, how separated the plates are. The bigger the plates, the more charge they can store, so more capacitance. The smaller the separation, the more charge they can store, so the bigger the capacitance. There's a similar equation, a corresponding equation, I should say, for a inductor, a simple inductor that looks just like a solenoid. So just like the parallel plate capacitor had a constant electrical field between the plates, a solenoid has a constant magnetic field in the windings, and so they are equivalents from the world of magnetism and electricity and the world of electrical and magnetic components. The inductance of a solenoidal inductor is given by the equation I've got on the screen there. It's, I'm looking for the pointer. This type of inductor with a certain number of turns per unit length, a certain length, and a certain cross-section. Those are the geometrical parameters for this inductor. Its inductance, its self-inductance, is given by this little equation here. So in the capacities case, you saw epsilon naught because it's an electrical device. Now you see mu naught because it's a magnetic device. In the capacitors case, you saw the geometrical properties of the parallel plate capacitor. In the inductors case, you see the geometrical properties of the inductor. Its number of turns per unit length, that's the lowercase l. Its cross-sectional area over which the magnetic field exists, that's the uppercase A. And the length of the solenoid, that's the cursive L here. Here's just an example, an illustration of using this equation. You can use this equation like we use the equation for a parallel plate capacitor. If I told you the geometry of a parallel plate capacitor, the size of the plates, the separation between the plates, you could go ahead and calculate its capacity, its ability to store charge. With this solenoidal inductor, if I give you the geometry of the solenoidal inductor, I give you the number of turns per unit length, or the number of turns. I give you the length of the solenoid. I give you the cross-sectional area of the solenoid. You can take that geometry and again calculate the inductance of the inductor, the self-inductance of the inductor. That tells you, how much flux you'll get when you drive a certain current through the windings of the inductor. Here's just an example of doing that. In this particular problem here, I've told you that we've got a solenoid, so that's telling you the geometry. Right? It's this coil of wire that are closely packed loops of wire. It has 200 turns total. It has 5 centimeters length. It has 4 square centimeters of cross section. So I've told you those pieces of information. I've told you the number of turns. So that's an uppercase N. N uppercase is the number of turns. N lowercase would be the number of turns per unit length. You'd have to divide the uppercase N, the number of turns, by the length of the solenoid to get the lowercase n, the turns per unit length. But anyway, I told you the number of turns. I told you the length of the solenoid also. That's the uppercase L in these equations. I told you the cross-section of the solenoid. And so you could go ahead and calculate with this equation here. You could go ahead and calculate the self-inductance, and that's what I just did down here. Now, let me just point out, with these little red arrows, right, there's 2 ways that you can write that equation. And that's where you've got to be careful about lowercase n's and uppercase n's. So you can write the inductance of the solenoidal inductor in terms of its total number of turns. That's writing the equation in terms of uppercase N. That's this version here. You could write the equation for the inductance of the inductor in terms of the number of turns per unit length. That's the turns per meter. That's the lowercase n, and that's equation here. So these 2 equations only differ in that one works in the language of total number of turns of the solenoid, which is what we happen to be given. The other one works in the language of number of turns per unit length, which in this case we didn't happen to be directly given. Both equations are completely correct. Both equations describe the inductance of an solenoidal inductor in terms of its turns or turns per unit length. You can just use one or the other as your preference, depending on whether you're given lowercase n or uppercase n. If you look at the equations, the fact that we're using lowercase n here corresponds to using uppercase L, the length of the solenoid, in the numerator. The fact that we're using uppercase n here means that we're using the length of the solenoid in the denominator. And that's just the algebra of replacing a uppercase n number of turns with a lowercase n, which is uppercase n over L. And so both equations are fine. One might be a little easier, one might be a little harder, depending on whether you're given the number of turns or given the number of turns per unit length. Okay. Last topic. Thank you. Energy in inductors, and energizing inductors and de-energizing inductors, and how much energy did they store? That's the last topic. So we're going to talk about powering up an inductor, powering down an inductor, and how much energy does the inductor store when it's powered up. We did this is an old story. It's not very original. We did it for capacitors. We talked about charging up a capacitor, discharging a capacitor, and how much energy did it store. And so we're following the same old route, but now in the forest of inductors rather than the forest of capacitors. This is a sketch of energizing an inductor. This is how you might energize an inductor. It's a sketch, basically, of the circuit that we demonstrated over here, where, in this case, the lamp is the resistor in this circuit. Anyway, I've got a battery, I've got a familiar resistor, and I got this new inductor. And I wired them up in series with a switch to make a complete circuit. If the switch is open, then no current is flowing in the circuit, no magnetic flux is passing through the inductor, and there's no energy stored in the inductor. If I close the switch, so at time 0 I'm going to close this switch. If I close this switch, suddenly there is a current flowing through the circuit. There's a current flowing through the resistor, there's a current flowing through the inductor. Suddenly there is a magnetic field, a magnetic flux through the windings of the inductor. The issue, the question here is, how do we get from there being no current in the circuit, no flux through the inductor, no field in the inductor, to the final current through the circuit, the final flux and final field through the inductor? We don't get there instantaneously. It doesn't take zero time. It's not instantaneous that we energize the inductor and get the full current through the inductor, get the full flux through the inductor. The reason is that we don't get the full flux, full current through the inductor at time 0, at that moment we close the switch, is because of the self-inductance. Because of the self-inductance, the inductor opposes the current flowing through it. Because of magnetic inductance. Because of inductance, the magnetic field that is created in the solenoid, in the inductor, will be opposed by a induced magnetic field to try and cancel it out. So magnetic induction, induced currents and induced fields oppose the change and causes the time to go from not being energized to fully energized. It causes it to take some period of time, some length of time, some duration of time, which looks like a clock tick for the inductor, for the particular inductor. So we're interested in how long it takes for the current to flow in through the inductor and the flux and the field to build up in the inductor. And that's the next slide. This is the moment on this graph here that we switch on the circuit. Over here on the left. Over here on the right, on the far right, would be the moment that the inductor is fully energized. So I'm plotting horizontally time, I'm plotting vertically the current in the circuit. We said we closed the switch at time 0, but we said because of self-inductance, because of induced EMFs, induced currents, we don't think the current will immediately ramp up to the full current that's given by Ohm's law for the resistance of the resistor in the circuit. It takes some time. Here you see that time, that evolution. 0 current initially. I0 is the final current of the fully energized circuit. the current has to build up due to self-inductance, due to induced EMFs, due to induced currents. The time scale for that build-up is determined by the inductance of the inductor, is determined by the resistance of the inductor. It's a ratio of L to R. It's a ratio of the inductance to the resistance. And so that is the time scale for that particular inductor in that particular circuit with that particular resistor to fully energize. It's like the clock tick of this resistor inductor circuits, like there was a clock tick for a capacitor resistor circuit. And so this is the time constant. It just means that if you have a large inductance, it's going to take a long time to energize it because it's in the numerator. If you have a small resistance, that allows a lot of current to flow. It's also going to cause a long time to energize that circuit because you've got to build up a large current in the inductor. So large inductance means it's going to take a long time because you get big induced effects. Small resistance is also going to take a long time because small resistance really means you've got to flow a lot of current. It's going to take a long time to turn that current up. So that's why it's L over R. Next two slides are the same pair of slides, but therefore not energizing an inductor when you switch the circuit on, but de-energizing an inductor by switching the circuit off, effectively. So here's the circuit here. Again, it's got our old friend, the battery, which energizes the circuit and the components in the circuit. That battery's initially in series with the inductor and resistor, and our complete circuit around the outside here is just the circuit we had before. It's just a fully energized inductor with the full current flowing through the resistor and inductor. But then I'm going to switch it off. I'm going to switch it off by switching from this position A to this position B, which effectively removes the battery from the circuit. So that switch is really in your head, just think, I've just pulled out the battery from the circuit and connected the resistor across the inductor. What's going to happen? Well, without the battery, we can't supply the energy to have the current flowing, so the current's going to turn on. So initially, before we flip the switch, in this case, we've got current flowing, we've got a fully energized inductor, we've got magnetic field, we've got magnetic flux in the inductor. After we flip the switch to the other position, we're going to get a de-energized inductor. We're going to get, there's nothing to sustain the current. We're going to get a zero field, zero flux in the inductor. But that doesn't happen instantly. That doesn't happen in a moment, again, because of in magnetic induction. If you try and switch that current off in the inductor, that inductor doesn't like that. It doesn't like having its current changed. It's going to try and replace that current with an induced current. If you try and switch off the magnetic field in the inductor, it doesn't like that also. It's going to try and replace that magnetic field with its own induced field. So when you switch the switch in the circuit to turn off, de-energize the inductor tries to keep going by inducing a current, keep going by energizing its own magnetic field. And that's the effect of magnetic inductance. So it's going to take some time to switch off this inductor, like it took some time to switch on this inductor. That time, you'll be pleased to know, well, as a graph, it looks like this. Again, this is the same sort of graph. It's time horizontally from the moment we flip the switch here to a long time afterwards when the circuit's completely de-energized. Vertically is the current that's flowing in the circuit. So the moment we close the switch, at that moment we still got that full current flowing in the circuit. It doesn't go to zero immediately. It gradually, exponentially goes to zero due to the effects of the self-induced current, the self-induced EMF. It takes some time to fall off. And that time constant, again, here's the equation. A time constant, I forgot to write the tau. This time constant here is the ratio of the inductance to the resistance. Here's tau. I wrote it over here. R is over L in this equation here because this is e to the minus t over tau. So that in the equation is e to the minus t over tau. Tau itself is L over R, and so 1 over tau is R over L. I probably just made that completely worse than it already was. Anyway, so again, if you've got a large inductor with a large inductance, it's going to take a while to switch it off, because it'll create large induced currents, large induced EMFs that'll maintain the magnetic energy in the inductor, maintain the current and magnetic field through and in the windings of the inductor. If you've got a small resistance, it's in the numerator of the time constant. Small resistance means there is a big current flowing in the circuit, big current in the inductor. Again, it's going to take a long while to turn it off because you've got to zero that large current. And the inductor will be opposing that, not want that to change. Okay, so that's time constants for that's time constants for energizing and de-energizing an inductor. It parallels a lot time constants for energizing and de-energizing a capacitor. The time constant for a capacitor involves the ratio of the capacitance and the resistance. This time constant involves the involves the product of the capacitance and the resistance. This time constant involves the ratio of the inductance and the resistance. But in both cases, the resistance and the capacitance, or the resistance and the inductance, determine the time constants. This was just a sort of appendix I put in there, because you might wonder, why on earth, this is a reasonable question, why on earth could inductance of an inductor divided by resistance of a resistor have units of time, give you a time constant? Why on earth could that be? It's just like the question, why on earth could the time constant of a resistor capacitor circuit, which involves capacitance and resistance, that time constant is RC, why on earth could that have units of time? Well, here's the answer to why L over R has units of time. There's a similar answer to why the time constant for a resistor capacitor circuit has units of time. And I just figured it out here. From Faraday's law, this is a rewriting of Faraday's law for the self-inductance. The self-inductance has units of volts, seconds over amps, just from the well-known units of current, amps, EMF, volts, and time, seconds. So this is just volts, seconds over amps. From Ohm's law, the units of resistance, well, the units of resistance are just volts over amps. L over R is the ratio of these units to these units. It's the ratio of the inductance to the resistance. That has units of seconds, because the volts, amps, and in inductance and the volt amps in resistance cancel one another out. So it does have, maybe surprisingly, it does have units of time. So an LR circuit does come with a characteristic clock tick, a characteristic time that describes it, describes how long it takes to energize or de-energize. I want to show you one last equation, the energy that's stored in an inductor. So this is last slide, I promise. Even I getting worn out by today's slides. And I have an enormous capacity for looking at slides like this. Okay, final equation. We met when discussing electricity, the energy stored in a capacitor. the energy stored in a capacitor you could write as 1/2 times the capacitance times the square of the voltage. That's one way of writing it. It said things like if you double the voltage between the plates of a capacitor, you'll quadruple the energy that's stored. There's a similar equation for the energy that's stored in an inductor. When we flow the current through the inductor, we're storing energy. When we stop it, we're de-energizing. The energy that's stored in an inductor depends on the current. It depends on the current in this way. It's 1/2 times the inductance of the inductor, not the capacitance of the capacitor, times the square of the current, not the square of the voltage. So it's a very similar equation. It also says that if you double the current flowing through your inductor, you'll quadruple the energy that's stored in the inductor. I'm going to end there. Today's class was all about transformer induction, like last class was about, motional induction.